So, dear friends, today we will discuss about the 7th lecture in module 1, where we are focusing on safety assurance and assessment. In this lecture, we will discuss about how to organize safety. Organizing safety can be well understood through an example. Nuclear radiation that has recently happened in Japan raised serious questions about safety, though the problem discussed now will not be directly applied to an oil and gas industry. However, an example of a recent occurrence will be interesting for us to know how safety in design and operation was well practiced in a nuclear power plant in Japan, from which we can learn good lessons. We will try to diagnose this case study and understand how safety is well organized in nuclear power plants in Japan. You can stop worrying about radiation disaster in Japan. I will tell you why from this example. Let us talk about the construction of Fukushima nuclear power plant in Japan, because to understand the design in safety and organizing safety in terms of process safety, let us try to first understand the construction technology and little bit about the process of nuclear power plants. The plants at Fukushima are also called as boiling water reactors. That is the type of process plant what they have for nuclear power plants in Fukushima. The process in this particular plant is as follows: nuclear fuel heats water, water therefore boils and creates steam, steam then drives the turbine that create electricity, steam is then cooled and condenses back to water, the water again is used, which is getting heated up by the nuclear fuel, therefore, the process is cyclic. Let us quickly understand, it is a very simple process. Nuclear fuel heats the water, water becomes steam, steam drives a turbine and generates electricity. Steam is then cooled and condensed back to water, it is recirculated for heating by the nuclear fuel, and the process is simply cyclic. The nuclear fuel used in this specific case is uranium oxide. Uranium oxide has got some specific chemical properties. Let us see what are they. Uranium oxide is a ceramic material with a very high melting point, it is about 3000 degrees centigrade. Fuel is manufactured in pellets. Pellets are nothing but small spherical balls. These pellets are put inside a long tube made of zircaloy. The melting point of zircaloy is about 2200 degrees centigrade and they are sealed in a tight packet. This assembly is technically called as fuel rod. These fuel rods are then subsequently put together in groups to form larger packages. These packages are subsequently put into the reactor and they are called as core. Let us talk about different containments in nuclear reactor. The first containment is the zircaloy casing. It separates the radioactive fuel from the rest because this is completely sealed tight. The second containment is the pressure vessel. The pressure vessel is designed to safely contain the core even at very high temperature. Friends, understand that core is nothing but packages of pellets which are put in a group and that becomes a core. The pressure vessel is usually designed to safely contain the core even when the temperature rises very high. Core is then placed in a pressure vessel. The third containment, that is the third layer of cover, is the third containment. This entire hardware of the nuclear reactor, the pressure vessel, all the pipes, pumps, coolant, essentially water, are then encased in the third containment. The third containment is generally airtight, which is sealed using a very thick bubble of the strongest possible steel. The third containment is therefore designed, built and tested with one unique purpose and objective: to contain indefinitely a complete core melted down uranium oxide pellets even when they melt down, though the melting temperature is about 3000 degrees centigrade, even when they melt down, the third containment is designed to contain them without leaking them out completely even when the core melts down. So, there is a very high test in the design itself, which is called safety by design. Now, we call this assembly as a core catcher. Now, why this is called as a catcher? If the core melts and the pressure vessel bursts, eventually it will catch the molten fuel and everything else, that is why it is called core catcher. For this purpose, a large and thick concrete basin is constructed under the pressure vessel. The pressure vessel, as we all know, is the second containment. A large and thick concrete basin is cast or constructed under the pressure vessel, which is subsequently filled with graphite all inside the third containment. This is where the core is catch. Now, let us talk about the reactor building. The third containment is now then surrounded by what we call as a reactor building. Reactor building is an outer shell that is supposed to keep the weather out, but nothing in. This is the part that was damaged in the explosion in the nuclear power plant in Japan. Before we understand how safety in design and how safety in operation was practiced in the specific power plant, let us try to understand fundamentals of nuclear reaction as a process, because if we do not understand this, at least in a very primitive level, we will not be able to appreciate the safety level management what they employ in the nuclear power plant in Japan. Let us see what are the fundamentals of nuclear reactions. The uranium fuel, which is used as in pellets, generates heat by nuclear fusion. Big uranium atoms therefore will be split into small atoms. They will generate heat plus neutrons. When neutron hits another uranium atom, it splits further, generating more neutrons and so on. This is called the nuclear chain reaction. Packing a lot of fuel rods next to each other would lead to overheating, because that is what you generally do. After about 45 minutes, this can result in melting of fuel rods itself. It is important to note, very important to note, that the nuclear fuel, which is uranium oxide in this specific case, in the reactor can never cause a nuclear explosion. I mean, there is no possibility that the nuclear fuel can become a nuclear bomb. In fact, to be very specific, building a nuclear bomb is actually a quite difficult process. It is not very easy. Therefore, please understand, friends, that the nuclear fuel used in this reactor can never become a nuclear bomb. So, there has been a misconcept, a miscommunication. So, there is no possibility that this could have become a nuclear explosion at all. Then how this happened? To understand this, let us take a parallel example, which is Chernobyl disaster of a nuclear power plant in Ukraine, which happened on 26 April 1986. The power plant photograph is shown on the right. In Chernobyl, explosion was caused by excessive pressure buildup, resulted in hydrogen explosion and ruptured all containments. After the containments have ruptured, it propelled the molten core material into the environment. That is how this became a disaster. Now, one can ask a question, why this did not happen in Japan, or possibly this will never happen in Japan. Let us see how. This is where I am emphasizing safety by design and safety by operation. Now, in order to control the nuclear chain reaction, just now we saw in the previous slide what is meant by nuclear chain reaction. In order to control this reaction, reactor operates use moderator rods. Then what is a moderator rod? The moderator rod actually absorbs the neutrons and kills the chain reaction instantaneously. So, if you use a moderator rod, this will intercept the chain reaction, it will abandon the chain reaction instantaneously. Therefore, a nuclear reactor is generally built in such a manner that when operating normal, you will take out all the moderating rods. The coolant water then takes away the heat and converts it into steam and electricity at the same rate as the core produces it. So, all this process happens simultaneously. In the normal operating procedure, the moderator rods will not be kept inside the container. Now, the challenge is that after inserting the rods and stopping the chain reaction, the core will be still keep on producing heat, because you cannot stop that heat production from the core. Okay, the moderator rods have disconnected the chain reaction, but the core is still keep on producing heat. Actually there is no reaction happening, but heat is there. This heat has got to be exaggerated. The uranium stopped the chain reaction, but a number of intermediate radioactive elements are created by the uranium during its fusion process, most notably cesium and iodine isotopes. They kept decaying and producing heat. Of course, this takes some time. Even though after the chain reaction is abandoned, there are some radioactive elements which are created by uranium, for example cesium and iodine isotopes. They will be decaying, of course, and while the decay process they will produce heat. Because they are not regenerated any longer from uranium, because uranium reaction has been stopped after the moderator rods are inserted in, they get less and less, and therefore the core cools down over a matter of days until those intermediate radioactive isotopes are used up. So, the cooling process will take some time, but it will cool up because the uranium has stopped from its reaction. This residual heat is causing headache generally. Let us see how this has been taken care of in the design in the Japan power plant. So, the first type of radioactive material, which is uranium in this case, which is a fuel rod, plus the intermediate radioactive elements that are uranium splits into are also inside the fuel rod. There is a second type of radioactive material created outside the fuel rod. So, there are two types now, one is inside the rod itself, one is outside the fuel rod. Let us see what is the main difference in the upfront in the design and safety in operation. The radioactive materials used in the plant have a very short half life. What does it mean is that they decay very fast and split into non radioactive materials maybe in seconds. So, we need not have to bother even with the discharge in atmosphere. So, if these radioactive materials, even when they are released into environment, radioactivity is released, but it is not dangerous at all. We must understand this first. Why? As they split up into non radioactive elements very fast, they become harmless, because there is a tendency that these elements will get split up into non radioactive elements very quick, maybe within seconds, and therefore they become harmless. Those radioactive elements are generally N16, the radioactive isotope of nitrogen. The others are noble gases such as xenon. Now, the question comes, where these elements come from? When the uranium splits, it generates a neutron. Most of these neutrons will hit other uranium atoms and keep the nuclear chain reaction going on, but some will leave the fuel rod and hit water molecules or air that is present in water. Then a non radioactive element can capture the neutron, it becomes radioactive. So, there is a catch here. Even though when the uranium splits and generates neutron, but some of them which leaves the fuel rod can hit water, come in contact with non radioactive element, and now they can become a radioactive element. But this will quickly get rid again to the neutron to return to its former within seconds. Even though the reaction is semi active, but still they will become harmless, because they will further split and become non radioactive very quickly, maybe within seconds. Now, let us apply this concept to Fukushima accident. Now, how this accident actually happened? It is very interesting to know that unfortunately in this power plant 3 disasters subsequently happened. One is the earthquake, followed by which is the tsunami, followed by which even the electrical standby failure has also occurred. Let us see how there has been third line of defense being planned in the design, which was successful in saving this plant, or at least saving the society from a major risk. The earthquake that hit Japan was 7 times more than the power which was expected than the worst earthquake that ever hit any nuclear power plant ever built in Japan. So, it is very unfortunate that the catastrophic reaction of this earthquake was 7 times very high compared to any earlier natural disaster earthquake occurred in Japan in the nearest vicinity where this power plant was constructed. When that earthquake hit, it was actually having a magnitude of 8.9 Richter. The nuclear reactors all automatically went into shutdown mode. So, the reactor went into shutdown mode. Within seconds after the earthquake started, the moderator rods have been inserted. Please understand, this is safety by design and operation, because even within seconds after the earthquake occurred, the moderator rods has been inserted. Please understand, moderator rods will always try to or attempt to kill the chain reaction and make the power plant automatically cool down, but cooling down of the plant is not instantaneous, it will take some time. So, within seconds after the earthquake occurred, moderator rods has been inserted into the core and the nuclear chain reaction of the uranium was stopped. So, one can say this is the first line of defense of safety by design. Now, the cooling system has to carry away the residual heat, because the reaction has stopped, but the heat is present. This heat has got to be regenerated and it has got to be cooled down. So, the cooling system which is present in the design itself has to carry away the residual heat which is generated inside the core. This residual heat is about 3% of the heat load under normal operating condition, that is the general anticipated value. But unfortunately, to operate the cooling system you need power, but earthquake destroyed the external power supply completely to the nuclear reactor. So, there is no external power supply possible to the reactor, therefore, the cooling system which was a part of the design was not in operation because earthquake destroyed the external power supply which goes to the reactor. So, cooling cannot take place. That is one of the most serious accidents for the nuclear power plant, because the cooling supply system was disrupted and accordingly a plant blackout has occurred, which received lot of attention when designing backup systems. Therefore, ladies and gentlemen, please understand, the focus generally should be safety by design. Safety by operation will follow only when there is success in safety by design. So, first you must evaluate your design for safety procedures. There are methods by which you can always evaluate the design, what we call as FMEA, failure mode effect analysis, which is one of the interesting design concepts for risk management, which we will discuss in the successive modules. But importantly here one should understand that focus should be always safety by design first. If this is achieved, then only safety by operation can be implemented. So, now the plant has gone into total blackout, there is no power supply to the reactor, earthquake has destroyed the power supply system, the power supply system has now interrupted the cooling system which is now required to cool down the system, because though the reaction is stopped because moderator rods were introduced, but the cooling is not happening because the heat cannot be controlled as there is no power supply. Now, the power is required to keep the coolant pumps working, you have no external power. Since the power plant had to be shut down, it cannot produce any electricity by itself. So, there is no supply of electricity also from the nuclear power plant, because nuclear power plant is stopped. Things were going on well for an hour. Okay. Subsequently, multiple sets of emergency diesel power generators were started to provide electricity. So, that is the second line of defense here. Now, generator which are diesel power driven are switched on to provide external power, which is artificial source of power, to the cooling supply system, which is now required to bring down the heat. Now, remember, the reactor is stopped by inserting moderator rods. Now, cooling system cannot be automatically on because there is no external power supply, because power supply was damaged because of earthquake. Now, within an hour people have switched on the multiple emergency source of diesel power generator were started to provide electricity. Now, here one can understand what would have been the delay, what would have been the procedural violation to switch on the diesel power, maybe not an hour, maybe after 30 minutes. So, there can be a study done here to understand the post accident scenario, so that this delay or the phase delay created between start of the diesel power plant or the diesel power source with respect to the power shutdown from the plant can be minimized. So, one can do a safety process assessment here, which can be done either doing an ASOP analysis or using an FMEA again. So, now let us understand the scenario. There is no external power, electricity is disconnected, nuclear reactor is stopped, heat is on, there is no radiation to be controlled, there is no power supply, external power supply is now switched on using a diesel power. Then came the second line of attack from the nature. Then came the tsunami, earthquake stopped, tsunami came, and the tsunami was much bigger than people expected when they building the power plant. So, now this again second disaster subsequently happened. Now, unfortunately friends, tsunami washed away all the multiple setback diesel generators kept on source. So, now you cannot generate power from the plant because plant is stopped. Though the plant is stopped, heat is still on. The cooler system cannot be on because there is no power supply. Earthquake spoiled the power supply and tsunami washed on the artificial power supply also. So, you see, safety by design can work only to some extent. Safety by operation then takes place, that is what I want to emphasize here. Though you have all second line of and third line of defense in the design, when all of them fail, how safety by operation can rescue the people around the plant, that is what you are going to see in this example. Now, tsunami came, diesel power systems were also washed away. Now, when designing a power plant in general, people will agree with me, there is always a philosophy called defense of depth. Now, let us see what is defense of depth. This means that you first build everything to withstand the worst catastrophe you can imagine. So, build everything to withstand the worst catastrophe you can imagine, and then design the plant in such a way that it can still handle one system of failure after the other. Remember, the defense of depth is possible only when the system failure occurs in sequence, but in this case earthquake and tsunami, which are natural disasters of very highest possible order, occurred simultaneously or more or less followed by one another, which was not expected. So, therefore, the defense of depth was in place in the design, but not very effective. Therefore, a tsunami taking away all the power backup in one swift is now an important scenario. The last line of defense is putting everything into third containment, because now the third containment, which is an external cover, is now at risk. This can contain everything, whatever the mess is, the moderate rods in or out, core molten or not, inside the reactor. If this third containment cracks, it becomes a serious problem. When the diesel generator failed after tsunami, the reactor operators switched to emergency battery power. This is where I say safety by process. Okay. Now, the reactor operators who were personnel working in the reactor should have an emergency response planning guidelines and training given to them, so that even at that moment of failure they were able to switch on the emergency battery power. That was the last line of defense they had. So, the batteries were designed as one of the backup systems to provide power for cooling the entire core for 8 hours. So, one can easily say here, this is one of the intelligent design done by the Japanese, which I say safety by design, and this was the one system what they had. They have trained the operator in such a manner, safety by process, and safety was an important line of defense in this example. After 8 hours, when the battery also ran out, the residual heat could not be carried away anymore, it is not possible. At this point, the plant operators begin to follow emergency procedures that are in place for loss of cooling event. Again, safety by operation. See, intelligently the people who have been working in the plant, even though the battery mode also ran out, that is exhausted after 8 hours, they try to operate some emergency procedures. It means if you are not imparted with necessary training for all emergency planning, you will not be able to act in such situation. So, safety by operation, safety by process is very important in such situation. The fuel failure will occur before the fuel melts and results from mechanical, chemical or thermal failures. The primary goal now at this moment is to manage the core while it is heating up, because it is heating up and I do not want this heating to continue, I want this to cool down. The reactor has number of independent and diverse cooling systems. safety be design again? Which one failed, which did not fail is not clear at this point of time. Therefore, friends, it is important that a detailed hazard study should have been conducted, or I think must have been conducted, which should tell me what is the sequence of the failure if one fails following the other. So, I do not know, this report is not available in the public domain. I do not know whether a detailed hazard study was carried out for this particular power plant after the failure or before the failure, but still I believe that a detailed hazard study would have at least imparted a good knowledge about the sequence of failure in such situations. Now, as long as the heat production exceeds the heat removal capacity, pressure starts increasing. There is a problem here. If you are not able to reduce the heat production compared to that of heat removal capacity what you have in terms of cooling system, this will result in pressure increase, and that will again start boiling water into steam, and steam will again become a problem, because in such situation can lead to explosion. Therefore, in order to maintain the pressure of a system at a manageable level, this steam which is being produced needs to be released from time to time. So, the reactor pressure vessel and the containment structure are designed with several pressure relief valves, what we call as PRVs. So, this is a point to be noted, friends, it is safety by design again. So, to protect the integrity of the vessel and the containment, operators started venting steam from time to time to control the pressure. So, this is by safety by training and operation and process. Some of these gases are radioactive fusion products, but they exist in a very small quantity. Of course, I will still strongly believe with you and agree that yes, some of the venting steam or few contain some radioactive gases, there is no doubt about it, but it is believed that they were in a small quantity. Therefore, when the operators started venting the system, some radioactive gases were released to the environment in a controlled manner. This is what we call emergency response planning and coordination, which is a very vital part on safety by training. Now, friends, while some of these gases are radioactive, they did not pose significant risk to the public safety to the workers on site. I will tell you how in the last slide. This procedure is justified, however, as the consequences are very low. Remember, risk, as we all now understand, is a product of magnitude and consequence. Now, one can say large amount of gases have been radioactive been released, even in that case the consequences caused with this release is very low, therefore, the risk put to the public safety is not very high, and therefore, it was justifiable, especially when compared to the potential consequences of not venting it out, because if you do not vent it out, it will result in pressure rise and that will lead to explosion. However, unfortunately in the Japanese case even explosion occurred. I will tell you how. Because instead of challenging the containment structure's integrity, at least the operators intelligently released the PRVs, and therefore they made the steam to escape in environment. However, I agree with you, these gases contain some radioactive components, but when compared to the consequences of the disaster of the containment itself, I would strongly agree that that was an intelligent decision. Remember, such decisions can come only when you have been trained for safety or you have been imparted education on emergency response planning guidelines. So, during this time mobile generators were transported to the site and some power was restored, more water was boiling off and being vented, that was being added to the reactor to cool down the reactor. This decreased the cooling capacity or the cooling ability of the remaining cooling systems. Of course, the remaining cooling systems which were only partially working were again relieved off because external water was being pumped in. Now, there is a problem here. You need lot amount of water, the amount of water required to cool the reactor is enormously high. At some stage during the venting process, the water level may even drop below the top of the fuel rod, and fuel rod is in a very high temperature, as high as close to 2200 degrees centigrade. So, they need to be cooled down. The temperature some of the fuel rod exceeded even 1200, initiating a reaction between the zircaloy and water. Zircaloy, remember, is the second level of containment. Even that started melting because the temperature is not coming down. Therefore, they wanted more water to cool down the reactor. Intelligently, this oxidizing reaction produces hydrogen gas because you are pumping water, which mixes with the gas steam mixture being vented, and the amount of hydrogen gas produced were really not known, but however, if there is enough hydrogen gas present, this could have resulted in explosion, and that happened. So, enormous amount of external water being pumped in the reactor resulted in this process of causing an explosion. So, at this point during the venting process, enough hydrogen gas was built up inside the containment. So, this was vented out to the air and explosion occurred. So, you can see the series of fault occurred. Earthquake started, earthquake damaged the reactor, it resulted in power shutdown, reactor was stopped, moderate rods introduced, there is no coolant supply available, external power was brought in, tsunami came, external power was damaged, there is no power backup available. After few hours, people brought up battery supply, even battery supply drained out, but they could stop the reactor, but they cannot stop the heat. They pump in water, they want to disable or relief of the cooling system. This water produced hydrogen gas release pressure, resulted in explosion. You see, these are all sequence of problems occurred at one plant. Though we are very unfortunate to know this happened in one part of the world which was a very advanced country, but still I am happy to know that this has at least give a good education system to understand how safety by design, safety by operation, safety in process was practiced by the Japanese to the core, so that they could contain this to the greatest possible extent without causing disaster to the society around the plant. Now, explosion resulted. The explosion took place outside the containment and inside and around the reactor building. Similar explosion occurred at unit 3 reactor as well. This explosion unfortunately destroyed the top and some of the sides of the reactor building, but it did not damage the containment structure or the pressure vessel. Remember, this is a very important appreciation I want to applaud to the Japanese, because it is a very interesting and very thorough design, and therefore I would applaud this as safety by design. Interestingly, understand, even after all defense systems of failure had occurred, even then the pressure vessel did not damage. So, one can appreciate really how the design was so strongly tested for its safety even at this stage of explosion. Therefore, this did not pose a risk to the plant safety structures at all. You can see the picture where the thick smoke has been generated and they are not able to control the heat. You can even see the blowing flames here, they are not able to control. This is after 13 hours of the earthquake and tsunami occurred. Let us see subsequently what happened. Since the fuel rod exceeded 1200 degrees centigrade, some fuel damage occurred. The nuclear material itself was still intact, but the surrounding zircaloy had started failing. At this time, some of the radioactive fusion products like cesium, iodine, etc. started to mix with the water and steam. To control this, they injected seawater. Since the reactor's cooling capability was limited and water inventory available in the reactor source was also limited, engineers decided to inject seawater mixed with boric acid, of course, a neutron absorber, to ensure the rods remain covered with water, because if they remain covered with water, can come down the heat, because the rods are now at a very high temperature of close to 1200 degrees centigrade. Now, I would say this as safety by operation, because they did not pump the seawater directly, they mixed seawater with boric acid, which is a neutron absorber, and then pumped in. But even then, injecting seawater will require more cleanup after the event, but provided cooling at that time to control the heat in the reactor. Of course, fortunately and successfully, this process decreased the temperature of the fuel rod to a non-damaging level. So, this is where they are pumping seawater to the plant to control the heat, and because the reactor has been shut down a long time ago, the decay heat has decreased to a significant lower level, pressure in the plant stabilized and venting was no longer required. That is how this was put to an end by the Japanese intelligence. Radiation levels at the Fukushima plant have been fallen to 231 microsieverts, which is equivalent to 23.1 millirem as of 2:30 p.m. March 14 local time. So, interestingly friends, you have understood the different lines of defense what this plant design had, the different levels of safety in design and operation what they have practiced, how the design was successfully done. Though this project or this case study is not related directly to oil and gas industry, being a process industry, understanding safety from such a very interesting example, I am sure would have enlightened you how safety by design, safety by operation, safety by training, emergency response planning guidelines would easily help people to act or to react in such emergency situation, so that the plant safety can be at least brought down to an acceptable level. Now, one interesting question to most of you is that what do we understand by the microsieverts? This is a unit to measure the radiation level. Let us see what is this, because that gives the completion for the lecture. Sievert is a derived term of ionizing radiation dose in SI units. It is a measure of health effect of low levels of ionizing radiation on human body. That is how the radiation effect on human body for ionizing radiation is measured actually. Sievert is used for radiation dose quantities such as equivalent dose, effective dose and committed dose. It is used both to represent the risk of the effect of external radiation from sources outside the body, as well as effect of internal radiation due to inhaled or ingested radioactive substances. The other unit millirem is an equivalent unit of sievert in CGS system. I hope friends you have enjoyed this lecture, because this gives a very interesting case study, the discussions what we had with my colleagues in IIT Madras, which will help us to have the clear understanding of post accident scenario. Ladies and gentlemen, my emphasis in this lecture is that how safety by design, safety by operation can be easily planned, and how hazard studies can be executed, so that advanced safety features or failure of safety measures can be anticipated and the design can be modified using FMEA, FMECA, hazard study and safety by operations. Thank you very much.